November 11th. Nordic Optical Telescope. La Palma, you're looking at raw data that shouldn't exist. A jet erupts from 3 I/Atlas, blasting material into space, and it's aimed directly at the sun. Not away from it. Toward it. Impossible. Every comet in 400 years of astronomy follows one unbreakable law. Solar radiation pushes tails away from the sun at 400 kilometers per second. No exceptions. Until now. This is the second time we've caught this sunward jet. Hubble saw it in July. Different telescope, different observers. Same result. In science. When the impossible repeats, it stops being an error and becomes something far more unsettling. Before we dive into what this means, if you're already hooked, go ahead and like this video and subscribe, but only if you genuinely want more investigations like this. Drop a comment and tell me where you're watching from right now, and whether your gut says extreme comet physics or something else entirely. Now, let's examine the image that's making astronomers question everything they know. The image sits on the screen in front of you, pixel by pixel, revealing something that shouldn't be there. It's 2:47 AM at the Nordic Optical Telescope's control room. The night shift astronomer has been tracking 3 I/Atlas for 6 hours straight, and now, as the final exposure completes its download, the room goes quiet. Not the comfortable quiet of routine observation. The uncomfortable quiet of witnessing something wrong. The telescope's 2.56 meter primary mirror has been locked onto coordinates that place 3 I/Atlas at 1.43 astronomical units from the Sun and 2.16 astronomical units from Earth. That's roughly 134 million miles from the Sun. About the same distance Mars orbits. The imaging region spans 500,000 kilometers, an enormous field of view necessary because whatever is happening around this object is happening on a massive scale. The exposure captures light that left 3 I/Atlas 17 minutes and 52 seconds ago, which means you're looking at the past, but a very recent past, and what you see makes no sense. There's a structure, a clear, prominent elongation in the coma, the fuzzy glow of gas and dust that surrounds the nucleus. It stretches outward at a position angle of 106 degrees, give or take 10 degrees of uncertainty. Position angles in astronomy are measured counterclockwise from north, so 106 degrees means this feature is pointing roughly east-southeast in the sky. The astronomer pulls up the ephemeris data, the calculated position of the Sun relative to 3 I/Atlas at the exact moment of observation. The projected sunward direction is 115 degrees. You read that twice. 106 degrees, 115 degrees, a 9-degree difference. In astronomy, that's not a difference. That's an alignment. The jet is pointing at the Sun. Let me put this in perspective. Imagine standing outside on a windy day holding a ribbon. The wind blows at 400 miles per hour, relentless, never stopping. Every single time you hold up that ribbon, it streams away from the wind. Always. Without fail, you've done this experiment 10,000 times, and 10,000 times the ribbon points downwind. Then, on the 10,001st try, the ribbon points into the wind, not slightly off, not at an angle, directly into the hurricane force blast. That's what you're seeing in this image. The solar wind at 3 I/Atlas's location is moving at roughly 400 kilometers per second. That's 894,000 miles per hour. Solar radiation pressure, the physical push of sunlight itself, adds to that force. Every comet, every single one we've studied since Edmund Halley first calculated a comet's orbit in 1705, obeys this rule. The tail points away from the Sun. Sometimes the tail curves. Sometimes it splits into a dust tail and an ion tail with slightly different geometries. But both tails always point generally away from the Sun. The physics is non-negotiable. Photons from the sun carry momentum. When they hit dust particles or ionized gas molecules, they transfer that momentum, pushing material outward. The solar wind, a stream of charged particles flowing from the sun, does the same thing. The combined force is powerful enough to push comet tails millions of kilometers into space. But not this one. This one is going the other way. You might be thinking, okay, maybe it's an optical illusion. Maybe we're seeing it from a weird angle. Fair question. Astronomers thought that too. Position angles can be tricky when you're dealing with three-dimensional structures projected onto a two-dimensional image. But here's the thing. This isn't the first sighting. July 21st, 2024. The Hubble Space Telescope, orbiting 340 miles above Earth, turned its instruments toward 3I/Atlas. Hubble doesn't just take pretty pictures. It's equipped with a wide-field camera 3 capable of imaging in wavelength from ultraviolet to near-infrared with extraordinary precision. The observation team, led by some of the most experienced comet researchers in the world, captured 3I/Atlas and immediately noticed something unusual, an anti-tail, a structure of material extending toward the sun instead of away from it. When that data first circulated among the astronomy community, the reaction was cautious. Anti-tails have been observed before, but they're rare and usually explained by geometry. Sometimes, when Earth passes through the orbital plane of a comet, we see the dust trail edge on, creating the illusion of a tail pointing sunward. It's a perspective effect, like seeing a stick appear bent when half submerged in water. The stick isn't bent, your perspective is just misleading you. But 3I/Atlas doesn't fit that explanation. The geometry is wrong. Earth's position relative to the comet's orbital plane doesn't create the necessary alignment. And now, 4 months later, the Nordic Optical Telescope has captured the same feature, same geometry, different position in orbit. Different observing team, different instrument, Dr. David Jewett, the astronomer who co-discovered the Kuiper Belt and has studied comets for over 40 years, was part of the team analysing the Nordic data. In the preliminary report, there's a line that stands out. The long-range jet structures evident in recent wide-field images are not visible in this data, likely due to the R-band filter used. Translation: the telescope was filtering out most of the gas emission lines, which means what you're seeing in this image is primarily dust. The densest, heaviest material, the stuff that should be the most susceptible to solar radiation pressure because it has more surface area relative to its mass. And it's still pointing at the sun. There's another detail in the image. A second, weaker asymmetry at position angle 301 degrees, that's pointing in the opposite direction. And when you check the ephemeris, it aligns almost perfectly with the anti-solar direction at 295 degrees. So now you have 2 jets, one pointing at the sun, one pointing away, both visible in the same frame. This isn't random. This is structure. This is symmetry. And symmetry in nature usually means something is driving it, something with a consistent energy source or mechanism. You lean back in your chair, and the question hits you, what could do this? Think about the forces at play. Solar wind and radiation pressure are pushing outward with immense force. For material to travel toward the sun against that pressure, it would need its own velocity, its own momentum, strong enough to overcome the outward push. That means whatever is ejecting this material isn't just passively venting gas from solar heating. It's actively launching it with enough speed to fight against a 400 km per second headwind. Comets do have jets. We've seen them countless times. The nucleus, the solid core of ice and rock, heats up as it approaches the sun. Subsurface ice vaporizes. Pressure builds, and gas erupts through cracks and vents in the surface, carrying dust with it. But those jets are driven by solar heating, which means they're strongest on the side facing the sun. The material gets caught by the solar wind and swept backward into the tail. The system is self-regulating. More sunlight means more outgassing, but also more radiation pressure to push that material away. For a jet to point at the sun, it would need to erupt from the night side of the nucleus, the side facing away from the sun where solar heating is minimal. That's possible in theory. Some comets do show asymmetric outgassing because their rotation exposes different areas to sunlight at different times, and subsurface heat can persist even when the surface cools. But for that material to maintain a sunward direction over millions of kilometers, that requires velocities far beyond what we typically see in comet outgassing. Here's where the numbers start to feel uncomfortable. The jet structures captured in earlier wide-field observations extend roughly 1 million kilometers toward the sun. To reach that distance against the solar wind, travelling at typical comet outgassing speeds of about 0.4 kilometers per second, the jet would need to have been continuously active for roughly 29 days. That's not a brief outburst, that's sustained, relentless output, and during those 29 days, the material is fighting against forces trying to shred it apart. You check the observation logs again, 3I/Atlas passed perihelion, its closest approach to the sun, on September 19th. That was 53 days before this November 11th image. So the object survived the most intense heating of its orbit, swung around the sun, and is still producing these jets. Post-perihelion activity isn't unusual for comets. Many remain active for months after their closest approach as subsurface ice continues to vaporize. But the geometry here is what's baffling. The sunward jet isn't a relic from perihelion. It's active now, pointing in a direction that defies the basic physics of how solar wind interacts with comet ejecta. Have you ever watched a fountain in strong wind? The water arcs upward, but the wind catches it and bends the stream. The stronger the wind, the more the stream distorts. Now imagine the wind is 1,000 times stronger, and the fountain is somehow maintaining a perfectly straight stream pointing directly into that gale. That's what 3I/Atlas is doing, and nobody can explain how. The data's solid. The observations are repeatable. The mystery is real. And as you sit there staring at the image, one thought crystallizes if this is a comet. It's unlike any comet we've ever studied, and if it's not a comet, well, that opens a door most scientists aren't quite ready to walk through yet. But ready or not, the data is leading us there, and the numbers we're about to examine make that door harder and harder to ignore. You remember your first astronomy class? The professor drew a simple diagram on the board, a circle representing the sun, a smaller dot representing a comet, and a long, swooping curve representing the tail. The tail always points away from the sun, she said, tapping the chalk against the board for emphasis. Always. This is as fundamental to comets as gravity is to planets. You nodded, wrote it down, and never questioned it. Why would you? The evidence was overwhelming. 400 years of observations. Thousands of comets. 0 exceptions. Until now. Let's go back to basics. Because to understand why 3I/Atlas is so disturbing, you need to understand exactly what should be happening, and why the universe seems to have ignored its own rulebook. Picture yourself standing on the surface of a comet. Not 3I/Atlas, not yet, just a regular, well-behaved comet cruising through the inner solar system. You're wearing a spacesuit, naturally, because the environment here is about as hospitable as standing on an iceberg in a blast furnace. The surface beneath your boots is a mix of water ice, carbon dioxide ice, frozen methane, and rock. It's porous, almost fluffy in places. With the density of styrofoam, the colour is dark, nearly black, because eons of radiation exposure have created a crust of complex organic molecules that absorb sunlight. It's cold, incredibly cold. At this distance from the sun, maybe 2 astronomical units out, surface temperatures hover around minus 100 degrees Fahrenheit in the shadows. But here's the thing, you're not in shadow. The sun is rising over the horizon of this tiny world, and when sunlight hits the surface, everything changes. The ice doesn't melt. There's no liquid phase here because the atmospheric pressure is essentially zero. Instead, the ice sublimates, transforming directly from solid to gas. Water molecules that have been locked in frozen matrix for billions of years suddenly gain enough energy to break free. They lift off the surface at speeds around 0.5 kilometers per second, carrying tiny dust particles with them. It's not a violent eruption. It's more like a gentle exhalation, a breath of ancient ice becoming gas and drifting upward. But then the solar wind hits. Imagine standing on a beach as a wave crashes over you. Now multiply that force by 1,000 and make it constant, never ending. The solar wind is a supersonic stream of charged particles, mostly protons and electrons, blasting outward from the sun at 400 kilometers per second. When those particles slam into the gas molecules lifting off the comet's surface, they transfer momentum. The gas molecules accelerate, reaching speeds of hundreds of kilometers per second, and they drag the dust particles along with them. At the same time, sunlight itself is pushing on the dust. Photons, despite having no mass, carry momentum. When a photon reflects off a dust particle, it transfers a tiny amount of momentum to that particle. One photon does almost nothing. But the sun emits an incomprehensible number of photons every second, and they add up. Radiation pressure becomes a tangible force, strong enough to overcome the comet's weak gravity and push dust particles away from the sun. The result is the tail, the beautiful, iconic tail that can stretch tens of millions of kilometers across space. Actually, there are usually two tails. The ion tail, made of ionized gas molecules, is pushed directly away from the sun by the solar wind and glows blue from fluorescence. The dust tail, made of larger particles less affected by the solar wind but more affected by radiation pressure, curves slightly as the particles inherit the comet's orbital motion while being pushed outward. Both tails point generally away from the sun. Always. Think about it like this. You're driving down the highway with your hand out the window. The wind pushes your hand backward, away from the direction you're moving. You can angle your hand, change its orientation, but the wind will always push it backward. There's no configuration, no trick of aerodynamics that makes the wind push your hand forward into the oncoming airstream. The physics doesn't allow it. That's why comet tails point away from the sun. The forces involved, solar wind and radiation pressure, push in one direction only outward. You can't flip a switch and make them push inward. You can't rotate the comet and change the geometry. The sun is the source. And the force radiates outward from that source in all directions, like spokes on a wheel. So when you see a tail pointing toward the sun, your brain does a double take. It's like watching that highway wind suddenly reverse and push your hand forward into the oncoming air. It violates causality. It breaks the rules. Now, I know what some of you are thinking. What about anti-tails? I've heard of those before. You're right. Anti-tails exist, and they've been photographed. Comet Arend-Roland in 1957 displayed a spectacular anti-tail that confused astronomers for weeks. But here's the crucial detail: those anti-tails aren't actually pointing at the sun. They're optical illusions. Here's how it works. Comets shed material continuously as they orbit, leaving a trail of dust particles along their orbital path. Most of the time, we see that trail from an angle, so it appears as part of the normal tail structure. But occasionally, Earth's orbit carries us through the plane of the comet's orbit, and we see the dust trail edge on. From that perspective, the trail appears as a spike pointing in whatever direction the comet's orbit is oriented. Sometimes, due to the geometry, that spike appears to point toward the sun. But it's not actually pointing toward the sun in three-dimensional space. It's pointing along the comet's orbital path, and we just happen to be viewing it from an angle that creates the illusion. Think of it like looking at a bicycle wheel from the side versus looking at it perfectly edge-on from the side. You see the spokes radiating outward, edge-on. You see a thin line. Same wheel, different perspective, completely different appearance. Astronomers are very good at accounting for these perspective effects. We have detailed orbital mechanics, precise calculations of Earth's position relative to every comet we observe, and software that can model exactly how geometric projection affects what we see. When the Hubble team observed 3I/Atlas in July, one of the first things they checked was whether the antitail could be explained by viewing geometry. They ran the calculations. The answer was no. Earth's position didn't align with 3I/Atelas's orbital plane in a way that would create a perspective-based antitail. And now, 4 months later, Earth has moved 120 degrees around its orbit. Our viewing angle has changed dramatically. If the July antitail was a geometric illusion, it should have disappeared or shifted significantly. Instead, it's still there, still pointing at the sun, still defying the fundamental physics of comet behavior. Let me give you another comparison. You know how a weather vane works? Right. The arrow points in the direction the wind is coming from because the tail catches the wind and swings the arrow around. It's a passive system. The wind dictates the orientation. Now imagine a weather vane that points into the wind. Arrow and tail both aligned with the oncoming gust. That's not how weather vanes work. That's not how physics works. But that's what we're seeing with 3I/Atlas. Doctor. Jane Liu, who co-discovered the Nordic optical telescope image with David Jewett, has spent decades studying Kuiper belt objects and comets. In an interview after the November observation, she was asked directly, could this be a measurement error? Her response was blunt. We checked everything twice. The position angle is solid. The solar direction is solid. The alignment is real. When a scientist of her caliber says the alignment is real, you don't brush it off. So here you are, standing on the surface of 3I/Atlas now. Not a normal comet. You feel the solar wind hitting you, a relentless pressure pushing against your suit. You watch as material erupts from vents in the ice beneath your feet, blasting upward, and then, impossibly, you watch it curve forward, toward the sun, into the wind, against every force that should be pushing it backward. What's driving it? What force is powerful enough to overcome solar wind and radiation pressure? What mechanism can sustain this output for months? These aren't rhetorical questions. These are the questions astronomers are asking right now, and the answers, the ones that fit the data, are starting to point toward possibilities that make people very, very uncomfortable. Because if the standard comet physics can't explain this, we need to look beyond standard comet physics. And once you step outside that framework, once you allow yourself to consider alternatives, the implications start to expand rapidly. But before we explore those alternatives, we need to confront the numbers. We need to see exactly how badly the math breaks down when you try to explain 3I/Atlas as a natural object. And trust me, the math doesn't just bend, it shatters. You're sitting at a desk now, calculator in hand, notepad covered in equations. The image of 3I/Atlas glows on your monitor, and you're about to do something astronomers do constantly: make the observations talk. Extract numbers from pixels, translate geometry into physics, and see if reality matches theory. Spoiler alert, it doesn't. Not even close. Let's start with what we can see. The Nordic optical telescope image shows two distinct jet structures. The sunward jet extends roughly 1 million kilometers from the nucleus toward the sun. The anti-solar jet stretches approximately 3 million kilometers in the opposite direction. These aren't estimates. These are measurements derived from angular size and known distance. 1 million kilometers sunward, 3 million kilometers anti-sunward. The distance from Earth to the Moon is 384,400 kilometers. The sunward jet is 2.6 times that distance. The anti-solar jet is nearly 8 times the Earth-Moon distance. Structures that dwarf the entire Earth-Moon system, emanating from an object Hubble measured at just 5.6 kilometers in diameter. Now here's where you start writing equations. For material to travel that far, it needs velocity and time. Typical comet outgassing velocities range from 0.3 to 0.5 kilometers per second. Let's use 0.4 kilometers per second. Divide 1 million kilometers by 0.4 kilometers per second, 2.5 million seconds. Convert to days, 29 days. The sunward jet would need continuous activity for 29 days to reach its observed length at typical speeds. But there's a massive problem. The sunward jet isn't travelling through empty space. It's travelling directly into solar wind moving at 400 kilometers per second. That's 1,000 times faster than outgassing velocity. Imagine jogging into a Category 5 hurricane. You're not making progress. You're being blown backward. For the jet to extend 1 million kilometers toward the sun, particles need to move significantly faster than 0.4 kilometers per second, but there's a ceiling. Outgassing velocity is limited by thermal energy, which depends on temperature. At 3 I/Atlas's distance, surface temperatures reach maybe 200 Kelvin under direct sunlight. At that temperature, carbon dioxide molecules cap out around 0.4 kilometers per second. You can't exceed that limit with passive solar heating. The physics doesn't allow it. You stare at your notepad and think, maybe the jet is so dense it punches through solar wind like a fire hose cutting through fog. Let's test that. The solar wind at 3 I/Atlas's location has about 6 protons per cubic centimeter, moving at 400 kilometers per second. You calculate dynamic pressure density times velocity squared. The result about 10 circumflex 9 pascals. For the comet's jet to push through, its dynamic pressure needs to be higher. Observations show the jet remains coherent out to 1 million kilometers, meaning its pressure must exceed solar wind pressure at that distance. Working backward, the jet needs a mass density of a few million proton masses per cubic centimeter. Now you calculate mass flux density times velocity times cross-sectional area. If the jet is roughly 1000 kilometers wide at 1 million kilometers out, the area is about 1 million square kilometers. The numbers pile up. When you crunch everything, you get a mass flux of approximately 5 billion tons per month. 5 billion tons per month. You lean back. 3 I/Atlas is ejecting the equivalent of a small mountain into space every 30 days. Continuously, for months. Where is all that mass coming from? Hubble measured 3 I/Atlas at 5.6 kilometers diameter. Assuming it's spherical, the volume is about 92 cubic kilometers. Comet nuclei typically have densities around 500 kilograms per cubic meter. Multiply volume by density total mass of roughly 46 billion tons. If it's ejecting 5 billion tons per month for 3 months since perihelion, that's 15 billion tons expelled. 1/3 of its total estimated mass gone in 3 months. Does it look like it lost 1/3 of its mass? No. Hubble's images show no dramatic change. The nucleus appears intact, stable, not fragmenting. The first prickle of real unease hits you. Let's talk energy. For ice to sublimate, you need heat. Carbon dioxide ice requires about 600 joules per gram. If 3 I/Atlas ejects 5 billion tons of CO2 per month, multiply mass by energy per unit mass, 5 billion tons equals 5 by 10 to 15 grams, times 600 joules, 3 by 10 to 18 joules required per month. Where does that energy come from? The sun. At 3 I/Atlas perihelion distance of 0.65 AU, solar flux is about 3200 watts per square meter. Post-perihelion at 1.4 AU, it drops to 700 watts per square meter. Let's use the higher value. To absorb 3 by 10 and 18 joules over 1 month, you need power input of about 15 10 now 12 watts at 200 watts per square metre. Divide power by flux required surface area of approximately 360 million square metres. That's a sphere with diameter of 10.7 kilometres. Hubble measured 5.6 kilometres. A sphere that size has surface area of about 98 million square metres. You're off by a factor of 3.7, and that assumes 100% of sunlight goes into sublimating ice. In reality, comets reflect light, radiate heat, lose energy through conduction. Typical comet nuclei absorb about 96% of incident sunlight. Even with high absorption, the energy budget doesn't close. You'd need the entire surface covered in pure actively sublimating ice with no rocky material, no crust, no dust. That's not how comets work. Observations show they're covered in dark, dusty crusts. Active regions typically cover only 10% to 30% of surface area. You're not off by factor of 4, you're off by factor of 10 or more. You try water ice. It requires even more energy, 800 joules per gram. Same calculation, and now you need a sphere with diameter of 23 kilometres. 23 kilometres, Hubble saw 5.6 kilometres. You're off by factor of 4 in diameter, which translates to factor of 16 in surface area. The numbers don't work. They don't come close. You try different assumptions. Higher outgassing velocity, internal heat from radioactive decay, unusual albedo. You run scenario after scenario, tweaking every parameter within reasonable bounds. None fix the discrepancy. Energy required exceeds energy available by an order of magnitude. Mass flux exceeds what the observed size can support. Geometry defies the forces that should dominate. Have you ever balanced your checkbook and found $1,000 missing? You go through every transaction assuming arithmetic error, but the numbers keep coming up the same. The money is just gone. That's what this feels like. Except instead of $1,000, it's the entire foundation of cometary physics. Dr. David Jewett wrote in his preliminary notes, given the scale of the jets reported, the fact that 3I/Atlas remains a single body is surprising if this is a natural comet. Surprising, a very polite way of saying, this doesn't make sense. You look at the image again. Jets are there. Measurements are solid. Calculations are correct. But the conclusion they point to makes your hands hesitate over the keyboard. If 3I/Atlas is a natural comet, the numbers should balance. Energy in equals energy out. Mass ejected correlates with size and composition. Geometry follows solar wind rules. None of that is happening, which means either our understanding of comet physics is fundamentally incomplete, missing some crucial mechanism, or 3I/Atlas isn't following comet physics because it isn't entirely a comet. That second possibility, hovering at the edge of every conversation, every analysis, every sleepless night staring at these images, is about to move from fringe to centre. Because when natural explanations fail, when every conventional hypothesis collapses under scrutiny, science demands we consider the unconventional, even if it makes us uncomfortable, especially if it makes us uncomfortable. You've been staring at equations for hours, and every path leads to the same dead end. The natural explanations don't work. So now you do what any good scientist does when the conventional fails, you start testing the unconventional. One by one, methodically, without bias, even if the hypotheses make you uncomfortable. Let's play detective. Let's take every possible natural mechanism that could explain 3I/Atlas's behaviour and put it through the ringer. If we're going to claim something extraordinary is happening, we need to eliminate every ordinary explanation first. That's how science works. No shortcuts. Hypothesis. 1. Hyperactive ice coverage. Maybe 3I/Atlas isn't like typical comets. Maybe its entire surface is covered in pristine, highly volatile ice with no dust crust. No inactive regions, just pure ice sublimating furiously under solar heating. You run the numbers. If 100% of the 5.6 kilometer diameter surface is active, releasing gas at maximum theoretical rates, how much material can it eject? You calculate the surface area, 98 million square meters. At perihelion, solar flux provides 200 watts per square meter. Assume perfect absorption and all energy goes into sublimation. Carbon dioxide sublimates at 600 joules per gram. You divide solar power by sublimation energy and scale it over the surface area. The maximum mass loss rate comes out to roughly 520 million kilograms per second at perihelion. That sounds like a lot. But remember, the jets need to sustain 5 billion tons per month, which is about 1.9 million kilograms per second. You're close, within a factor of 3, which feels promising until you remember one critical detail. No comet has 100% active surface area, ever. Rosetta spacecraft observations of Comet 67P showed that even at perihelion, only about 6% of the surface was actively outgassing. Other comets studied in detail show active fractions between 5% and 30% maximum. Why? Because solar heating creates a dust mantle, a layer of non-volatile material left behind as ice sublimates. This mantle insulates the ice beneath, reducing further sublimation. It's a self-regulating process. For 3I/Atlas to have 100% active surface, it would need to continuously shed that dust mantle faster than it forms. That requires mass loss rates even higher than what we're already trying to explain. You've created a circular problem. This hypothesis lasted about 15 minutes under scrutiny. Hypothesis 2, exotic ices. Okay, maybe it's not water or carbon dioxide. Maybe 3I/Atlas is rich in even more volatile ices. Carbon monoxide sublimates at temperatures below 25 Kelvin. Nitrogen ice sublimates below 63 Kelvin. These ultra-volatile ices can outgas at distances where water ice remains frozen. You adjust the calculations. Carbon monoxide ice requires only 200 joules per gram to sublimate, compared to 600 for carbon dioxide. That means you can eject 3 times more mass with the same energy input. Suddenly the energy budget looks more manageable. But there's a problem. Spectroscopic observations of 3I/Atlas haven't detected the emission lines characteristic of carbon monoxide or nitrogen. When these gases sublimate and get ionized by solar UV radiation, they emit light at specific wavelengths. Those signatures should be visible if they're present in large quantities. They're not. You could argue that maybe our spectrographs missed them, that the signal-to-noise wasn't high enough. But here's the bigger issue: objects rich in ultra-volatile ices should be extremely active, even at large distances from the Sun. They shouldn't wait until perihelion to start outgassing. 3I/Atlas was detected at 9 AU from the Sun, well beyond the snow line where even carbon dioxide remains frozen. If it were rich in carbon monoxide or nitrogen ice, it should have been blazingly active from the moment we spotted it. It wasn't. Its activity ramped up as it approached the Sun, consistent with water and carbon dioxide ice, not ultra-volatiles. This hypothesis lasted 20 minutes. Hypothesis 3. Radioactive heating. What if solar heating isn't the only energy source? What if 3I/Atlas has a radioactive core, isotopes decaying and generating heat from within? This is how some moons in the outer solar system stay warm enough to host subsurface oceans. Maybe the same principle applies here. You calculate how much radioactive material would be needed. The required power output is about 1 baud to 10 to 12 watts to sustain the observed mass loss. Radioactive decay of uranium, 238-1 of the most common long-lived isotopes, produces about 95,000 joules per kilogram per year. Convert that to watts, roughly 0.003 watts per kilogram. To generate 1 by 10 nad 12 watts, you'd need approximately 3 bucket 10 watt of 14 kilograms of uranium. That's 300 trillion kilograms. The entire estimated mass of 3I/Atlas is only 46 billion kilograms. You'd need the object to be 500 times more massive than it appears, or essentially pure uranium. There's no natural process that creates a uranium sphere flying through interstellar space. Uranium forms in supernova explosions and gets mixed into planetary systems during formation, but it's always diluted among other elements. The highest natural concentrations found on Earth are in uranium ore deposits, which are maybe 20% uranium by mass, not 100%. This hypothesis collapsed in under 10 minutes. Hypothesis 4. Subsurface heat reservoir. Maybe 3I/Atlas formed recently in a collision and still retains heat from that impact, or maybe it has a subsurface ocean of liquid water, insulated by an ice shell, slowly releasing energy. You think about the timescales. For a subsurface ocean to persist, the object needs either recent formation or ongoing heat input. 3I/Atlas is travelling on a hyperbolic trajectory from interstellar space. It's been in the cold void for potentially millions of years. Any primordial heat from formation would have radiated away eons ago. Impact heating possible. But where's the evidence impacts large enough to melt interiors typically fragment objects or at minimum leave visible scars? Hubble's images show no obvious impact features, no fragments trailing the nucleus, no signs of recent catastrophic collision. Subsurface ocean heated by tidal forces that works for moons orbiting giant planets. Where gravitational flexing generates heat. 3I/Atlas isn't orbiting anything, it's on a solo journey through the solar system. No tidal heating? You tried to make the numbers work anyway, assuming some exotic thermal reservoir. But even if such a reservoir existed, how does it translate to directional jets? Heat diffuses? It doesn't create asymmetric, sustained outflows pointing toward and away from the sun with remarkable precision. This hypothesis felt weak from the start and didn't improve with examination. Duration 12 minutes. Hypothesis 5. Spin induced jetting. What if 3I/Atlas is spinning rapidly and centrifugal force is flinging material into space? Some asteroids rotate fast enough that loose material on their surfaces can escape. Maybe the jets are just spin-off from a tumbling nucleus. You look up the rotation period. Observation suggests 3I/Atlas rotates once every few hours, typical for objects its size. You calculate the centrifugal acceleration at the equator. For a 5.6 kilometer diameter object rotating every 3 hours, the centrifugal acceleration is roughly 0.0005 meters per second squared. The escape velocity from 3I/Atlas's surface is about 3 meters per second. Centrifugal force provides nowhere near enough energy to eject material at escape velocity, let alone accelerate it to speeds capable of fighting solar wind. Also, spin-induced jetting would create a disk or equatorial spray, not two precisely aligned jets pointing toward and away from the sun. The geometry doesn't match. This one died quickly. Duration 8 minutes. You lean back in your chair, rubbing your eyes. 5 hypotheses, 5 failures. And these aren't fringe ideas. These are reasonable, physics-based mechanisms that should work if 3I/Atlas were behaving like a natural object experiencing unusual but explainable conditions. None of them fit. Here's the thing about science, it's not about clinging to explanations because they're comfortable or familiar. It's about following the data wherever it leads. When you eliminate the possible and find yourself left with the improbable, you don't ignore the improbable, you investigate it. Dr. Avi Loeb, the Harvard astrophysicist who's been studying 3I/Atlas closely, said in the recent interview, When you have an object that doesn't behave like any natural comet we've studied, you have two choices. Either invent new physics to make it natural, or consider that it might not be entirely natural. Both require evidence. Both deserve serious investigation. That's where you are now, standing at a crossroads. One path leads to unknown natural mechanisms, exotic physics we haven't discovered yet. The other path leads to something that makes most scientists deeply uncomfortable but can't be dismissed without examination. Because if the energy doesn't come from the sun, if the mass flux exceeds what the observed size can provide, if the geometry defies the forces we know are acting on the system, then maybe, just maybe, there's an additional force we haven't accounted for, an artificial force, an engineered one. And that possibility, the one that's been lurking in the background of every failed hypothesis, is about to step into the light. You're standing at a door you never expected to approach for your entire career, maybe your entire life. You've understood science as the study of natural phenomena. Stars form from collapsing gas clouds. Planets coalesce from protoplanetary disks. Comets are dirty snowballs left over from solar system formation. Everything has a natural explanation rooted in physics, chemistry, and time. But what happens when nature stops making sense? What happens when every natural explanation you test crumbles under the weight of the data you open the door? The room on the other side isn't filled with wild speculation or science fiction fantasies. It's filled with engineers, physicists, and a single question. If this object were designed, what would it be doing? Let's be absolutely clear about something. Considering an artificial hypothesis doesn't mean abandoning science. It means applying the same rigorous standards we use for natural phenomena to the possibility of technology. We don't believe first and gather evidence later. We propose a testable hypothesis, make predictions, and see if observations match those predictions. So here's the hypothesis 3. I/Atlas is not entirely a natural comet. Some component of its behaviour, specifically the sunward jet, is the result of an artificial mechanism, not magic, not aliens beaming down from flying saucers, engineering, technology. A device operating according to physical laws we understand, just applied in ways we haven't built ourselves yet. What kind of device produces thrust without rockets? You know the answer because we've already built them here on Earth. Solar sails, light sails, structures that use photon pressure from sunlight to generate propulsion. Here's how they work. Photons from the sun carry momentum. When a photon hits a reflective surface and bounces off, it transfers twice its momentum to that surface. 1 unit from the initial impact, 1 unit from the reflection. It's a tiny force per photon, but sunlight contains an incomprehensible number of photons. Spread that force over a large, lightweight surface, and you get measurable acceleration. Japan's Ikaros spacecraft demonstrated this in 2010, deploying a 14-meter diagonal sail and successfully using solar radiation pressure to adjust its trajectory. The Planetary Society's Light Sail 2, launched in 2019, raised its orbit using nothing but sunlight pushing against a 32 square meter sail. These aren't theoretical concepts. These are working technologies. The advantage of a light sail is that it requires no fuel, the sun provides the energy, the sail provides the surface area. The physics does the rest, for interstellar travel, where carrying fuel becomes prohibitively expensive due to mass. Light sails offer an elegant solution. Accelerate on the way out of your home star system, coast through the interstellar void, and then use the target star's light to decelerate on arrival. Now here's where it gets interesting. Most light sails are designed to accelerate away from the star. Photons push the sail and the spacecraft moves in the direction of that push, outward, away from the light source. That's the intuitive configuration. But what if you wanted to decelerate? What if you were approaching a star at high velocity and needed to slow down? You angle the sail. Picture a sailboat. When the sail is perpendicular to the wind, the boat is pushed directly downwind, but angle the sail and you can tack at an angle to the wind, even making progress into the wind by zigzagging. Light sails operate on similar principles. The direction of thrust depends on the sail's orientation relative to incoming photons. If you orient a light sail to reflect photons at an angle, the resulting thrust vector has components both perpendicular to the photon direction and critically opposite to your direction of travel. You're using the star's radiation pressure to brake. It's counterintuitive, but the physics is sound. The sail doesn't point directly at the star. It's angled such that reflected photons produce a net force that opposes your velocity. The result from certain viewing angles, particularly from the side. It looks like material is being ejected toward the star. Not because the sail is physically emitting particles in that direction, but because the optical signature of the sail, the reflected sunlight and perhaps ablated material from the sail's surface, creates a plume-like structure aligned with the braking thrust vector. You sit down and start calculating. If 3I/Atlas has a light sail component, how big would it need to be solar radiation pressure at 1.4 astronomical units? 3I/Atlas's current distance is about 4 micronewtons per square meter. That's an absurdly small force. To generate enough thrust to create the observed jets, you'd need significant surface area, but here's the key: you don't need thrust to eject material. You need the appearance of ejection. The sunward jet could be the optical signature of reflected photons and material ablating from the sail's surface due to intense solar heating. The anti-solar jet could be actual outgassing from the comet nucleus. Behaving normally, what you're seeing isn't two jets from one object. It's one natural jet and one artificial optical signature, combined in a single image. Breakthrough Starshot, a research initiative aimed at sending lightweight probes to Alpha Centauri, has proposed light sails with surface areas of 16 square meters and masses of just a few grams. The surface-to-mass ratio is critical for effective acceleration or deceleration. You want maximum area with minimum mass. If 3I/Atlas has a deployed sail structure with an area of, say, 1000 square kilometers, incredibly thin, perhaps nanometers thick, the mass could be relatively small compared to the comet nucleus. The sail wouldn't dramatically increase the object's total mass, but it would drastically change its optical properties and how it interacts with solar radiation. Does this sound far-fetched? Maybe. But is it more far-fetched than a 5.6 kilometer comet nucleus generating energy output that requires a 23 kilometer surface area? Is it more far-fetched than ejecting 1/3 of its mass in 3 months without visible fragmentation, Doctor? Avi Loeb has been saying this for years, since Oumuamua first challenged our assumptions in 2017. Extraordinary claims require extraordinary evidence, but so do extraordinary natural phenomena. If an object behaves in ways that require exotic, never-before-seen natural mechanisms, that's also an extraordinary claim. We should investigate both possibilities with equal rigour. The scientific community pushed back hard against Loeb's suggestions about Oumuamua. Peer reviews called his light sail hypothesis speculative, premature, insufficiently grounded, and maybe they were right to be cautious. One anomalous object doesn't overturn decades of established science. But now there's a second object. 3I/Atlas, exhibiting different anomalies but similarly resistant to conventional explanation. At what point does anomalous become pattern? At what point do we admit that maybe, just maybe, Not every object passing through our solar system is natural. Here's the uncomfortable truth: we have no comprehensive survey of interstellar objects. Before 2017, we'd never detected one. Now we've found 2 in 7 years. Our detection methods are still rudimentary, biased toward large, bright objects passing close to Earth. How many smaller, fainter objects have slipped past unnoticed? And here's the even more uncomfortable question: if technological civilizations exist elsewhere in the galaxy, if they've developed spacefaring capabilities, wouldn't some of their probes or derelict spacecraft eventually drift through our neighborhood? Space is vast, but it's also old. Billions of years old. Even slow-moving artifacts have time to cross immense distances. The Drake equation estimates the number of active, communicative civilizations in our galaxy based on star formation rates, planet occurrence, and the probability of life. But there's another factor rarely discussed: the longevity of technological artifacts. Spacecraft, probes, and light sails don't die when their craters do. They keep drifting, potentially for millions of years, long after the civilization that built them has vanished. If even a fraction of technological civilizations in galactic history sent out exploratory probes, the galaxy could be littered with ancient, non-functional hardware slowly migrating through interstellar space. Most would be too small or too cold to detect. But occasionally one might pass close enough to a star to light up, to outgas if it's collected interstellar ice, to behave in ways that look almost natural but not quite. You look at the 3I/Atlas image again, and suddenly it doesn't just look strange, it looks deliberate. The sunward jet isn't chaotic, it's structured, persistent, aligned. The dual jet geometry suggests intentional configuration, not random outgassing. What if you're not looking at a comet? What if you're looking at a comet with a passenger and natural nucleus that's been travelling through space for eons, accumulating ice, and somewhere attached or embedded in that ice, a sail, a probe, a remnant of technology from a civilization that may no longer exist? It's been braking, slowing down as it approaches the sun. That's why the sunward jet appears post-perihelion. That's why the alignment is so precise. It's not fighting physics, it's using physics, just in ways designed rather than accidental. And if that's true, if there's even a chance that's true, then December 19th isn't just another observing opportunity. It's potentially the most important moment in human history, because we're about to get our closest, clearest look at something that might answer the oldest question we've ever asked. Are we alone? You're in the engineering lab now, drafting blueprints for something that might already exist. Not building it, just trying to understand how it could work. Because if 3I/Atlas has a light sail, if that's the explanation for the impossible jets, then the engineering tells you what to look for. It gives you predictions, testable predictions. That's how you turn speculation into science. Let's build a light sail capable of doing what we're seeing. First, the basics. A light sail needs to be large, lightweight, and reflective. The surface-to-mass ratio determines how much acceleration you get per unit of radiation pressure. The higher the ratio, the better. For interstellar travel, you're talking about materials measured in atoms thick. Graphene, for example, is a single layer of carbon atoms arranged in a hexagonal lattice. It's incredibly strong for its weight, highly reflective if properly treated, and thin enough that you can pack enormous surface areas into minimal mass. Your hypothetical sail needs to survive the journey. Interstellar space is harsh. Cosmic rays bombard anything travelling between stars. Micrometeoroids, tiny grains of dust moving at kilometres per second, punch holes through thin materials. A sail that left its origin star system thousands or millions of years ago would be damaged, degraded, partially destroyed. It wouldn't be pristine. It would be a wreck, barely functional, holding together through redundancy and over-engineering. Now, the size. If you want to decelerate an object with a mass of 3 I/Atlas's nucleus, roughly 46 billion kilograms, using solar radiation pressure at 1.4 astronomical units, you need substantial area. Solar pressure at that distance is about 4 micronewtons per square metre. To generate meaningful deceleration over months, you'd need something on the order of hundreds to thousands of square kilometres. That sounds absurd until you remember that the material can be nanometers thick. 1,000 square kilometres of graphene 1 nanometer thick has a mass of only about 400 kilograms. That's less than a car. Attached to a 46 billion kilogram comet nucleus, it's a rounding error in total mass, but it dominates the object's interaction with light. Here's where the geometry gets fascinating. The sail doesn't need to be a perfect circle or square. It could be irregular, torn, partially collapsed. Maybe it deployed successfully millennia ago but has since been shredded by impacts. What remains is a tattered structure, still reflective enough to interact with sunlight, still large enough to produce observable effects, but no longer symmetrical or pristine. That irregularity could explain the dual jets. If the sail is angled to produce braking thrust, reflecting photons in a way that creates the sunward optical signature, and simultaneously the nucleus beneath it is outgassing normally from solar heating, you'd see both features, one artificial, one natural, overlapping in the same field of view. The sail's orientation matters. For braking, you angle the sail so reflected photons have a component of momentum opposite to your direction of travel. Picture holding a mirror at 45 degrees to incoming sunlight. The light bounces off at 90 degrees to its original path. The mirror feels a force perpendicular to the incoming light. That force has components both perpendicular to and opposite your velocity vector. You're converting photon momentum into deceleration. From Earth's perspective, looking at this configuration from the side, the reflected light and any material ablating from the sail's surface under intense solar heating would appear as a structure extending toward the sun. Not because material is physically travelling sunward against the solar wind, but because the optical signature of reflection and ablation aligns with that geometry. You sketch the scenario. The sail, possibly tens of thousands of kilometres across when fully deployed, is now fragmented. Sections have torn away. What remains is still substantial, still functional enough to interact meaningfully with solar radiation. The nucleus, a natural comet, sits at the centre of this structure, outgassing as any comet would. The sail breaks, the nucleus vents. The two processes create the complex morphology we're observing. How do you test this? What predictions does the light sail hypothesis make that differ from the natural comet hypothesis? First, spectroscopy. If the sunward jet is reflected sunlight from a metallic or carbon-based sail, its spectrum should match the sun's spectrum almost exactly. Reflected light is just solar light bouncing off a surface. It doesn't gain or lose spectral features unless the surface absorbs specific wavelengths. In contrast, a natural comet jet emits light from excited molecules, gas that's been ionized by solar UV radiation and is fluorescing at characteristic wavelengths. Carbon monoxide, carbon dioxide, water, cyanogen, each produces distinct emission lines. Hubble and the Nordic Optical Telescope used broadband filters, capturing light across wide wavelength ranges. That's excellent for imaging but limited for detailed spectroscopy. To test the light sail hypothesis, you need high-resolution spectra of the sunward jet. Does it show emission lines consistent with ionized gas? Or is it pure reflected continuum? Second, polarization. Reflected light from a flat or structured surface tends to be polarized. Natural sunlight is unpolarized. But when it bounces off a reflective sail, the electric field vectors align preferentially. Measuring the polarization of light from the sunward jet would reveal whether it's reflected or emitted. Comet gas emissions are typically unpolarized. Reflected light from a sail would show significant polarization. Third, temporal variability. If 3I/Atlas is rotating and the sail is attached or tethered to the nucleus, the orientation of the sail relative to the Sun and to Earth changes over time. That should produce periodic variations in brightness and geometry. The sunward jet's intensity should fluctuate with the rotation period. Natural outgassing can also vary with rotation, but the pattern would differ. A sail's reflectivity depends on angle of incidence. Gas emission depends on which parts of the nucleus are illuminated. Fourth, thermal emission. A light sail absorbs some solar radiation and re-radiates it as infrared. The amount depends on the sail's albedo and temperature. A highly reflective sail stays cooler and emits less infrared. A degraded sail, darkened by interstellar dust accumulation, absorbs more and emits more. Infrared observations with instruments like the James Webb Space Telescope could detect thermal emission from the sail distinct from the nucleus's thermal signature. And fifth, trajectory. This is the big one. If 3I/Atlas has a functional light sail producing thrust, its trajectory should deviate from a purely gravitational orbit. It should accelerate or decelerate in ways not explainable by solar gravity and radiation pressure alone. Astrometric measurements, precise tracking of the object's position over time, would reveal non-gravitational forces acting on it. Oumuamua showed exactly this behavior. Its trajectory deviated from predictions, accelerating away from the Sun faster than gravity alone could explain. The conventional explanation invoked outgassing, jets of gas pushing the object like tiny rocket engines. But Oumuamua showed no visible coma, no tail, no evidence of the outgassing that supposedly explained its acceleration. That discrepancy is what prompted Loeb to propose the light sail hypothesis in the first place. 3I/Atlas is active. It has a visible coma and tails, so outgassing is definitely happening. And that complicates the analysis. Separating thrust from a hypothetical sail and thrust from natural jets requires precise measurements and detailed modelling. But it's not impossible. If the non-gravitational acceleration is larger than what the observed outgassing can explain, if it persists even when outgassing diminishes, that's evidence for an additional thrust source. You look at the engineering requirements and realise something striking. Building a functional interstellar light sail is not beyond plausible technological capability. It's ambitious. Yes, it requires materials, science and engineering precision we're only beginning to develop. But it's not magic. It doesn't violate physics. It's just very, very difficult. Breakthrough Starshot estimates that with current or near-future technology, we could build light sail probes and accelerate them to 20% the speed of light using powerful ground-based lasers. The sails would be meters across, weigh grams, and carry tiny payloads of sensors and transmitters. Launch 1,000 of them toward nearby star systems, and statistically, some would arrive intact. Now imagine a civilization that reached this capability 1,000,000 years ago. They launch probes, thousands or millions of them, exploring their stellar neighborhood. Most fail, some succeed, a few drift beyond their intended targets and keep going, coasting through the galaxy, accumulating ice and dust over eons, eventually resembling comets more than spacecraft. Then one day, one of these ancient probes falls into a solar system. Our solar system. The sail, battered but still partially functional, begins interacting with our sun's radiation. The ice it's accumulated sublimates, creating a coma. From a distance, it looks like a comet, but up close under scrutiny, the details don't quite add up. The geometry is wrong. The energy budget fails. The jets point the wrong direction, and a young species on the third planet from that star, a species just beginning to explore its own solar system, points its telescopes at this visitor and asks, "What are you?" That's where we are. That's the moment you're living through. December 19th isn't just an observation date, it's a rendezvous, humanity's best instruments, aimed at an object that might be the first unambiguous evidence of extraterrestrial technology ever detected. Or it might be a comet with really weird physics. Either way, the data will tell us. That's the beauty of science. You don't need to believe, you just need to measure. December 19th. You've circled the date on your calendar, set reminders on your phone, maybe even cleared your schedule. In just over a month from the November 11th Nordic observation, 3I/Atlas will reach its closest approach to Earth, not closest to the Sun. That already happened back in September. This is closest to us, the moment when our telescopes get their best view, when the distance shrinks to just over 80 million kilometres, roughly half the distance from Earth to the Sun. 80 million kilometres sounds far, and it is, but in astronomical terms, that's practically next door. Close enough for Hubble to resolve surface features if they exist. Close enough for the James Webb Space Telescope to capture infrared spectra with unprecedented detail. Close enough for ground-based observatories to track position changes accurate to milliarc seconds, revealing the tiniest deviations in trajectory. You're not just watching anymore. You're hunting for evidence that could answer the question definitively. Let's talk about what's actually going to happen that day and in the weeks surrounding it. Because this isn't a single observation at a single moment. It's a coordinated campaign involving multiple telescopes, multiple wavelengths, and multiple teams of researchers, all focused on one object, the James Webb Space Telescope. Humanity's most powerful infrared observatory has been allocated observing time for 3I/Atlas. JWST sits at the L2 Lagrange point, 5 million kilometres from Earth, permanently shielded from the sun's glare by its massive sun shield. Its 6.5 metre segmented mirror collects infrared light with sensitivity that makes Hubble look like a pair of binoculars. When JWST points at 3I/Atlas, it won't just take pretty pictures, it will dissect the object's thermal signature. Infrared observations reveal temperature. Different materials emit infrared radiation at different wavelengths depending on how hot they are. A rocky nucleus covered in dark dust absorbs sunlight and re-radiates it in the mid-infrared. Ice sublimates and cools the surface, creating temperature gradients. And a light sail, if one exists, should have a distinct thermal profile. Highly reflective materials stay cooler because they absorb less sunlight. Degraded materials heat up more. JWST's spectrometers will break down that infrared light into its component wavelengths, creating a spectrum. From that spectrum, you can identify specific molecules. Water ice has absorption features at certain wavelengths. Carbon dioxide has different features. Organic molecules, silicates, metals, each leaves a fingerprint. If the sunward jet is composed of ablated sail material, graphene or some other carbon structure heated to high temperatures, the spectrum will show it. What are you hoping to see? Anomalous carbon signatures, temperatures inconsistent with passive solar heating, emission patterns that don't match known comet compositions. Hubble will be watching too. Its ultraviolet and visible light cameras will capture high-resolution images as 3I/Atlas makes its close pass. Hubble's been doing this for decades, observing comets, asteroids, and distant galaxies with unmatched clarity. The advantage Hubble has over ground-based telescopes is its position above Earth's atmosphere. No atmospheric turbulence, no weather, no light pollution, just clean, sharp images. The goal with Hubble is morphology, shape, structure, symmetry. If the sunward jet changes orientation as 3I/Atlas rotates, Hubble will catch it. If the jet's intensity varies, Hubble will measure it. If there's any hint of extended structure, something that doesn't fit the profile of a point source nucleus, Hubble will resolve it. You imagine the Hubble team uploading the raw images to their servers, astronomers around the world downloading them within minutes, running enhancement algorithms, adjusting contrast, isolating features. Somewhere in these pixels might be the outline of something artificial. Or it might just be a fuzzy blob, indistinguishable from 1,000 other comets Hubble has photographed. Ground-based telescopes are joining the effort. The European Southern Observatory's Very Large Telescope in Chile, the Keck Observatory in Hawaii, the Gemini telescopes, all have 3I/Atlas on their target lists. These instruments lack the resolution of Hubble but compensate with size and versatility. Large mirrors collect more light, enabling spectroscopy of faint features. Adaptive optics systems correct for atmospheric distortion, sharpening images to near space-based quality. Spectroscopy is the priority for ground-based observations. You need to know what the jets are made of. Are they normal comet outgassing, water vapour and carbon dioxide? Or something else? The sunward jet, in particular, needs detailed spectroscopic analysis. If it's reflected sunlight, the spectrum will be continuous, matching the sun's blackbody curve with no emission lines. If it's ionized gas, you'll see bright lines at specific wavelengths corresponding to excited molecules. Sodium, potassium, cyanogen, hydroxyl radicals all produce characteristic colours when energized by solar UV radiation. Their presence or absence tells you what's happening in that jet. Polarimetry is another tool in the arsenal. Several observatories plan polarimetric observations, measuring how light from 3I/Atlas is polarized. Reflected light from a smooth surface becomes polarized. Scattered light from irregular dust grains has a different polarization signature. Emitted light from gas is usually unpolarized. By analyzing polarization, you can distinguish between reflection, scattering, and emission. If the sunward jet shows high linear polarization, that's a strong indicator of reflected light, consistent with a light sail. If it shows low or random polarization, that supports the natural outgassing hypothesis. And then there's astrometry, precise positional measurements over time. Multiple observatories will track 3I/Atlas's position against the background stars with extreme accuracy. Any deviation from a purely gravitational trajectory will show up as a residual, a difference between where the object should be and where it actually is. Oumuamua's non-gravitational acceleration was detected this way. Observers noticed it was moving slightly faster than solar gravity predicted. The deviation was small, just a few millimeters per second squared, but it was real and measurable. For 3I/Atlas, the same technique applies. If a light sail is producing thrust, even minimal thrust, it will alter the trajectory in detectable ways. The challenge is separating sail thrust from outgassing thrust. Natural jets produce recoil forces. When gas erupts from the nucleus, Newton's third law applies: action and reaction. The gas flies one direction, the nucleus gets pushed the opposite direction. Comet 67P, studied extensively by Rosetta, exhibited measurable non-gravitational acceleration from outgassing alone. So how do you tell the difference? You model the outgassing based on observed activity levels, calculate the expected thrust, and compare it to the measured trajectory deviation. If the deviation exceeds what outgassing can explain, you've got evidence for an additional force. If the deviation matches outgassing predictions, the light sail hypothesis takes a hit. December 19th is not the end of the observation campaign, it's the peak. The moment of closest approach provides the best conditions, but observations will continue for weeks afterward as 3I/Atlas recedes. You want to track its trajectory over as long a baseline as possible to minimize measurement uncertainties. You want multiple spectra to see if composition changes with time or distance from the sun. You want photometry to monitor brightness variations and correlate them with rotation. Every data point matters. Every measurement constrains the models. Every spectrum eliminates possibilities or reinforces them. Here's what keeps you awake at night. What if the data is ambiguous? What if JWST's spectra show unusual features but not definitively artificial ones? What if Hubble sees asymmetries that could be interpreted either as sail structure or irregular outgassing? What if the trajectory shows non-gravitational acceleration, but the magnitude is consistent with intense outgassing from a hyperactive nucleus? Science rarely gives you clean, unambiguous answers. Real data is messy. Measurements have uncertainties. Instruments have limitations. Competing explanations often fit the same observations almost equally well, and choosing between them requires subjective judgment about which model makes fewer assumptions or which is more physically plausible. The Oumuamua debate exemplifies this. Loeb argued the non-gravitational acceleration and lack of visible outgassing pointed to a light sail. Critics countered that outgassing could be invisible if the composition was primarily hydrogen or nitrogen, gases that don't produce bright emission lines. Both explanations fit the data, neither could be definitively ruled out. The argument continues to this day. 3I/Atlas might go the same way, or it might not. The difference here is activity. We can see 3I/Atlas outgassing. We have spectroscopic data showing what molecules are present. The natural comet explanation has more constraints, more things it needs to match. That makes it easier to test and potentially easier to falsify. If the observations in December show that natural processes can account for everything, the light sail hypothesis dies. Not because we want it to, but because the evidence doesn't support it. That's how science works. Hypotheses live or die based on data, not preferences. But if the observations reveal something that doesn't fit, something that requires invoking new physics or admitting the presence of technology, then the conversation shifts dramatically. You check the countdown timer on your screen. 29 days until December 19th. 29 days until the data floods in. 29 days until we know if we're looking at the most anomalous comet in history or the first confirmed piece of extraterrestrial technology humanity has ever encountered. Either way, the universe is about to get a lot more interesting. You step back from the telescope, the equations, the engineering diagrams. You walk outside and look up at the night sky. Somewhere out there, invisible to your naked eye but real and measurable, is 3I/Atlas, a tiny speck of ice and rock, maybe more, travelling through our solar system at thousands of kilometres per hour. And suddenly the enormity of what you're contemplating hits you. This isn't just about one weird comet anymore. This is about everything. Let's zoom out. Let's think about what it means, really means, if we confirm that 3I/Atlas has an artificial component, not just for astronomy or physics, but for humanity's entire understanding of its place in the cosmos. For thousands of years, humans have asked the same question: are we alone? Every culture, every civilization, every generation has looked at the stars and wondered. Ancient Greeks speculated about plurality of worlds. Medieval scholars debated whether God created life only on Earth. Modern scientists calculate probabilities using the Drake equation, estimating how many technological civilizations might exist in our galaxy right now. The numbers vary wildly depending on your assumptions. Optimistic estimates put thousands or millions of civilizations in the Milky Way. Pessimistic estimates suggest we might be the only one, or one of very few. We don't know. We've searched for radio signals for decades through SETI programs, listening for artificial transmissions from distant star systems. We found nothing conclusive. But here's the thing about radio searches. They assume civilizations want to communicate or are actively broadcasting. What if most civilizations are quiet? What if they use communication methods we haven't thought of? Quantum entanglement or neutrino beams or something we won't discover for another century. What if they existed millions of years ago, thrived, sent out exploratory probes, and then went extinct before we evolved to ask these questions? Radio silence doesn't mean absence. It just means we're not hearing them right now, in the specific ways we're listening. Searching for physical artifacts is different. Technology persists. A probe launched 1 million years ago doesn't care if its craters are still alive. It keeps going, following its programmed trajectory or drifting after its mission ends. Space doesn't corrode things the way planetary atmospheres do. There's no rust, no weathering, no biological decay. A spacecraft in the vacuum of interstellar space could remain recognizable for billions of years. Frank Drake, the same astronomer behind the Drake equation, once estimated that if technological civilizations regularly send out probes, and those probes have typical lifespans and velocities, the galaxy could contain millions of artifacts right now. Most would be derelict, non-functional, drifting aimlessly. But they'd still be there. Physical evidence that someone else figured out spaceflight and decided to explore. We've never found one. Not definitively. But until 2017, we'd never systematically looked. We didn't have the instruments to detect interstellar objects passing through our solar system. Oumuamua was discovered almost by accident, caught by the Pan-STARRS Survey Telescope in Hawaii, which was designed to search for near-Earth asteroids, not interstellar visitors. Now we're looking. The Vera Rubin Observatory, currently under construction in Chile, will begin operations soon and will scan the entire visible sky every few nights, detecting objects far fainter and smaller than anything previous surveys could find. The estimates suggest Rubin will discover 1 interstellar object per month once it's fully operational. 1 per month, 12 per year, over a decade. That's 120 new interstellar visitors to study. Most will probably be natural. Comets and asteroids ejected from other star systems during planetary formation. But if even a small percentage are artificial, if 1 in 100 or 1 in 1,000 is a probe or derelict spacecraft, we'll find them, and that changes everything. Think about the Fermi paradox. Enrico Fermi, during a lunch conversation in 1950, reportedly asked, "Where is everybody?" The logic is straightforward. The galaxy is old, about 13 billion years. Earth formed 4.5 billion years ago, relatively recently in cosmic terms. If intelligent life is common, some civilization should have arisen billions of years before us, even travelling at a tiny fraction of light speed. They'd have had time to colonize the entire galaxy multiple times over. So where are they? Why don't we see evidence of vast interstellar empires? Dyson spheres around stars, megastructures, fleets of spacecraft. There are dozens of proposed solutions to the paradox. Maybe intelligent life is incredibly rare. Maybe civilizations self-destruct before achieving interstellar travel. Maybe they're deliberately avoiding us. A galactic zoo hypothesis where Earth is a nature preserve. Maybe they transcend physical form and exist in dimensions we can't perceive. Or maybe they're here, in the form of ancient artifacts, and we just haven't recognized them yet. If 3i/Atlas is artificial, it provides one data point, one piece of evidence that technological civilizations exist, or existed, and that they built things capable of crossing interstellar space. That single data point doesn't tell you how common such civilizations are, but it tells you they're not impossibly rare. It tells you the universe is, or has been, populated with beings who looked at the stars and decided to reach them. That has profound implications for the Drake equation. Several terms in that equation are pure guesses. The fraction of planets that develop life. The fraction of life-bearing planets that develop intelligence. The fraction of intelligent species that develop technology capable of interstellar communication. We have a sample size of 1us. Every estimate is extrapolation from Earth. Finding extraterrestrial technology gives you a second data point. Suddenly, you're not extrapolating from one example. You're beginning to build a statistical sample. If two technological civilizations exist within detectable range, that suggests the galaxy has hosted many more over its history. And then there's the philosophical weight. For all of human history, we've been unique. The only known example of intelligence, consciousness, art, science, morality, every philosophy, every religion, every ethical system has been constructed around the assumption that humans are special, possibly the only minds in the universe capable of asking why. What happens when that assumption breaks? Some people would find it terrifying. The realization that we're not central, not unique, that intelligence is a common phenomenon that arises wherever conditions permit. It's humbling in a way that's hard to articulate. You look at all of human achievement, Shakespeare and Einstein and the Apollo missions, and you realize it's just one example among potentially millions. Nothing we've done is singular. Someone else, somewhere else, probably did it first and better. Others would find it inspiring. The loneliness of being the only intelligent species, the existential isolation of looking at a silent universe, would end. We'd know we're part of a broader community, even if that community is scattered across time and space, and we'd know that curiosity, exploration, the drive to understand the cosmos. These aren't unique to humanity. They're universal traits that emerge when matter organizes itself into thinking beings. There's also the question of what we could learn. If 3I/Atlas contains functional technology, even degraded technology, studying it could leapfrog our own development. Material science, propulsion systems, energy generation, communication methods. Any piece of working hardware would be a treasure trove of engineering insights. We've experienced this before on Earth. When European explorers encountered advanced metallurgy in the Americas, or when cultures traded technologies across continents, both sides learned and adapted. The difference here is the knowledge gap could be millions of years. Imagine Bronze Age humans discovering a modern smartphone. They couldn't replicate it, couldn't even fully understand it, but they could learn principles that would accelerate their own technological progress. Of course, there's risk too. Technology isn't neutral. It can be used for creation or destruction. If we discover an advanced propulsion system, do we use it to explore the galaxy peacefully, or do we weaponize it? History suggests humans are very good at turning discoveries into tools of war. And there's the possibility that whoever built 3I/Atlas, if it is artificial, might still be out there. Maybe not actively monitoring their ancient probes, but existing somewhere. Potentially aware that one of their artifacts has entered another civilization's solar system. Do they care? Will they check on it? Could our observations of 3I/Atlas inadvertently announce our presence to someone who'd rather we remained unnoticed? Most scientists dismiss these concerns as premature. We don't have confirmed extraterrestrial technology yet. Worrying about first contact before we've even verified the existence of others is putting the cart before the horse. But the questions linger because the implications are so vast. Dr. Avi Loeb has argued that this is precisely why we should be investigating these possibilities now. Before a discovery is made, we need frameworks, ethical guidelines, international agreements on how to handle detection of extraterrestrial technology. We need protocols for data sharing, for verification, for announcing findings to the public without causing panic. Right now, we have none of that. If a telescope operator captures definitive evidence tomorrow, there's no established procedure. Do they call NASA the United Nations posted on Twitter? The lack of preparedness is a vulnerability. You look back up at the sky. The stars are the same stars humans have seen for millennia, but your understanding of what might exist among those stars has changed. 3I/Atlas has forced the conversation into the open. It's made the question of extraterrestrial artifacts not a fringe topic for late-night speculation, but a legitimate scientific inquiry demanding serious resources and attention. Whether 3I/Atlas turns out to be natural or artificial, that shift in perspective is permanent. The next interstellar object we discover will be scrutinized with the same rigor, the same openness to unconventional explanations, and the one after that, and the one after that. We're no longer assuming everything out there is natural. We're testing, we're investigating, and that's how you find answers, not by declaring what must be true based on limited data, but by remaining open to what might be true and following the evidence wherever it leads. December 19th approaches. The data will come, and humanity, whether it's ready or not, might be about to learn something about the universe that changes us forever. You got the science, you got the engineering, you got the philosophy. Now let's talk about the bet, because Dr. Avi Loeb didn't just write papers and give lectures about 3I/Atlas and Oumuamua. He put his reputation on the line in a way most scientists never do. In early 2024, Loeb made a public wager. He bet that within 5 years, by 2029, we will find undisputable evidence of extraterrestrial technology, not radio signals from distant civilizations, not microbial life on Mars, physical artifacts, manufactured objects, technology built by non-human intelligence. 5 years, that's the timeline. The clock is ticking. When news of the bet spread through the astronomy community, reactions were mixed. Some colleagues called it publicity seeking, accused Loeb of prioritizing headlines over rigorous science. Others admired the boldness, the willingness to make a falsifiable prediction and stake his credibility on it. But here's what most people miss. The bet isn't really about winning or losing. It's about forcing the conversation by setting a deadline. Loeb transformed a vague, distant possibility into something concrete and measurable. 5 years means specific observing campaigns need funding now. It means telescope time needs allocation now. It means graduate students can build careers studying interstellar objects without being dismissed as fringe researchers. The bet creates urgency, and urgency drives discovery. Let's break down what needs to happen for Loeb to win. Undisputable evidence is the key phrase. Not ambiguous data that could be interpreted multiple ways. Not anomalies that require exotic natural explanations. Clear, definitive proof that an object we observe was manufactured by intelligent beings. What would that look like? Probably not a smoking gun in the form of alien writing or obvious mechanical components. Space is harsh. Anything travelling through interstellar space for thousands or millions of years would be degraded beyond easy recognition. But there are signatures technology can't hide. Geometric regularity. Natural objects are lumpy, irregular, asymmetric. Manufactured objects, even damaged ones, show patterns, straight edges, repeated structures, symmetries that don't occur in nature. If high-resolution imaging reveals these features on 3I/Atlas or another interstellar visitor, that's strong evidence. Material composition. Certain alloys and compounds don't form naturally. If spectroscopy detects materials that require industrial processes to create elements combined in ratios that geological or astrophysical processes can't produce, That's a signature of technology. Artificial isotope ratios. Nuclear reactors and certain manufacturing processes alter the natural abundance of isotopes. On Earth, enriched uranium has a different isotopic signature than naturally occurring uranium. The same principle applies to any technological artifact. Detect anomalous isotope ratios in an interstellar object, and you found something that didn't form through natural nuclear synthesis. Modulated signals. If an object emits radio waves, light, or other electromagnetic radiation with patterns that suggest information encoding, that's technology. Natural processes produce noise. Technology produces signal. The challenge is getting close enough to make these measurements. 3I/Atlas at closest approach will still be 80 million kilometers away. That's too far for detailed surface analysis. You can get spectra, you can measure trajectory, you can resolve large-scale structures, but you can't see the fine details that would definitively prove artificial origin. That's why Loeb has been advocating for intercept missions. Don't just observe from Earth. Send a spacecraft to rendezvous with the next interstellar object we detect. Get within meters or kilometers. Deploy cameras, spectrometers, magnetometers. Sample the surface if possible. Bring back physical evidence. It sounds like science fiction, but it's technically feasible. NASA and ESA have both studied concepts for rapid response missions to intercept interstellar visitors. The main challenge is time. These objects move fast and don't give much warning. By the time we detect them, they're often already past their closest approach and heading back out of the solar system. Oumuamua was discovered on its way out. We had weeks to observe it before it became too faint. A spacecraft launched at that point would have taken years to catch up. 3I/Atlas gave us more lead time because it was discovered farther out. But still, mounting an intercept mission requires years of planning and billions of dollars. Unless we get lucky. Unless the next interstellar object is detected early, on its way in, giving us months or years to prepare a mission. The Vera Rubin Observatory changes the game here. Its wide-field survey will detect objects farther out, earlier in their approach. That gives mission planners time to design, build, and launch an interceptor. If Rubin discovers an anomalous interstellar object in 2026 and data suggests it might be artificial, you can bet there will be political and financial pressure to send a probe. Imagine the images. A spacecraft approaching 3I/Atlas or a similar object. Cameras capturing close-up views, revealing details no Earth-based telescope can resolve, seeing whether the sunward jet is reflected light from a sail or something else entirely, measuring magnetic fields, particle fluxes, surface temperature gradients, maybe even deploying a lander. That's the dream scenario. That's what would settle the question beyond doubt. But let's be realistic. 5 years is a tight timeline. Getting from discovery to confirmed artificial origin requires multiple steps. Detection. Initial observations ruling out natural explanations. Securing funding for detailed follow-up. Analyzing data. Peer review. Independent verification. Consensus building. Science moves slowly. Extraordinary claims face extraordinary scrutiny, as they should. Even if we photograph a clearly artificial structure tomorrow, the process of confirming it, ruling out every conceivable natural or instrumental artifact explanation, would take months or years. So what happens if December 2029 arrives and we haven't found undisputable evidence? Does Loeb lose the bet? Does that mean we're alone after all? Not necessarily. Absence of evidence over 5 years doesn't prove extraterrestrial technology doesn't exist. It just means we haven't found it yet, or we haven't recognized it. The search could take decades or centuries. The galaxy is vast. Artifacts could be rare. Our detection methods might still be too crude. Loeb himself has acknowledged this. He said the bet is less about winning or losing and more about changing how the scientific community approaches the question. Before Oumuamua, the idea of searching for alien artifacts in our solar system was fringe. Now it's mainstream enough that major observatories allocate time to it, that NASA funds studies on intercept missions, that graduate students write dissertations on it. That's progress. That's the real victory, regardless of whether we find definitive proof by 2029. But here's the thing. You're living through this. You're watching the bet play out in real time. December 19th is one milestone. The Vera Rubin Observatory coming online is another. Every new interstellar object discovered is another roll of the dice. And dice, when you roll them enough times, eventually land on outcomes you didn't expect. You think about the odds. If 1% of interstellar objects are artificial, and Rubin detects 12 per year, you'd expect roughly one artificial object every 8 years. 5 years might not be enough. Or it might. Probabilities are tricky. Sometimes you get lucky early, sometimes you don't. What's your gut tell you? Do you think Loeb wins the bet? Do you think 3I/Atlas is the one? Or will it be some future object we haven't detected yet? Or do you think 5 years will pass, and we'll still be debating ambiguous data, still arguing over whether anomalies are exotic comets or ancient technology? Personally, you're not sure. The scientist in you says wait for the data, don't speculate. Let the measurements decide. But the part of you that looks at the stars and wonders, that part is hoping that within 5 years, maybe sooner, we'll know, really know, that we're not alone, that intelligence is a cosmic phenomenon, not a terrestrial fluke. December 19th won't answer that question definitively, but it might nudge us closer. And every nudge matters when you're trying to solve the oldest mystery humanity has ever faced. The telescope images will arrive, the spectra will be analysed, the measurements will be published, and then what? Regardless of what December 19th reveals, regardless of whether 3I/Atlas turns out to be the most bizarre comet ever studied or humanity's first encounter with extraterrestrial technology, one thing is certain: we've already changed. The conversation has shifted. Permanently. Before Oumuamua in 2017 suggesting that an astronomical object might be artificial was career suicide for most scientists, you'd be labelled a crackpot, denied tenure, laughed out of conferences. The scientific community had an unwritten rule: natural explanations only. Don't invoke aliens unless you've exhausted every conceivable natural possibility. And even then, don't. That rule made sense historically. For centuries, humans attributed things they didn't understand to gods, demons, supernatural forces. Science arose by rejecting those explanations and insisting on natural mechanisms. Lightning isn't Zeus throwing bolts, it's electrical discharge. Diseases aren't divine punishment, they're microorganisms. The discipline of assuming natural causes has served us extraordinarily well. But there's a difference between assuming natural causes and refusing to consider alternatives when natural causes fail. When your calculations require a comet to be 4 times larger than it appears, when the geometry defies every physical force acting on the system, when hypothesis after hypothesis collapses under scrutiny, at what point does clinging to it must be natural become dogma rather than science? 3I/Atlas has forced that question into the open, not because Loeb is loud or controversial, though he is both, but because the data is genuinely weird, genuinely difficult to explain. And when established scientists like David Jewett and Jane Liu, people who've spent careers studying comets and distant solar system objects, publish observations showing jets that shouldn't exist, the fringe becomes mainstream. Now, when the next interstellar object is discovered, the first questions won't just be what's its composition and what's its trajectory. There'll also be, does it show anomalies, and could it be artificial? That's new. That's a fundamental shift in how astronomy approaches these objects. The Galileo Project. Loeb's initiative to systematically search for technological signatures in astronomical data has raised millions in funding. Universities are hiring researchers to develop detection algorithms for non-natural objects. Graduate students are building careers on this question without being dismissed as fringe. The infrastructure is being built right now to take the search seriously, and infrastructure matters. When you have dedicated telescopes, funded researchers, and established protocols, you find things you'd otherwise miss. SETI, the search for extraterrestrial intelligence, has been listening for radio signals since the 1960s. They haven't found definitive evidence yet, but the act of searching has advanced radio astronomy, developed signal processing techniques, and kept the question alive in the public consciousness. The search for extraterrestrial artifacts will do the same. Whether we find anything or not, the techniques we develop, the instruments we build, the data we collect, all of it advances our understanding of the solar system, interstellar space, and the kinds of objects that traverse the galaxy. But let's talk about what happens if we do find something. If not 3 I/Atlas, then the next object, or the one after that. If 5 years from now, or 10, or 20, we get images that show unmistakable geometry, spectra that reveal artificial materials, trajectory deviations that can't be explained by natural forces, what then? First, verification. No single observation will be enough. Multiple telescopes, multiple teams, independent analysis. The data will be scrutinized with intensity that makes peer review look casual. Every alternative explanation will be tested. Instrumental artifacts, data processing errors, natural phenomena we haven't considered. The bar for claiming this is artificial is extraordinarily high, and rightly so. If the evidence survives that scrutiny, if consensus emerges among experts that yes, this object shows signs of technology, the announcement would be historic. Not in the hyperbolic sense we use that word today, but genuinely, permanently historic. One of those moments like the first powered flight, the moon landing, the discovery of DNA structure, a before and after moment for human civilization. The immediate questions would be practical. Is the object still functional? Can we communicate with it? Is it transmitting data somewhere? Can we learn from its design? Should we attempt to retrieve it? And the broader questions would be philosophical. Who built it? When are they still out there? Why did they send it? Was it targeted at our solar system specifically? Or is it a random derelict that happened to pass through? You might never get answers to those questions. An ancient, non-functional probe wouldn't tell you much about its creators except that they existed and achieved spaceflight. But even that limited information changes everything. It tells you technological civilizations aren't impossibly rare. It tells you the universe has been, and possibly still is, populated with intelligences that looked at the stars and reached for them. It tells you we're part of a story much larger than we realized. There's also the scenario where the data remains ambiguous, where December 19th gives us more information but not definitive answers. Where 3 I/Atlas continues to defy easy categorization, natural or artificial, that's frustrating but also valuable. Ambiguity drives further research, keeps the conversation going, it motivates better instruments, more detailed observations, refined models. Oumuamua is still debated. Papers continue to be published arguing both sides. Some researchers remain convinced it's an unusual comet. Others think the light sail hypothesis fits better. The data doesn't definitively settle it, and that's okay. Science doesn't always give clean answers quickly. Sometimes you need more data, Sometimes you need decades of accumulation before patterns become clear. What you've learned through this journey with 3I/Atlas is that the universe is stranger than our models predict. Whether that strangeness is natural or artificial, it's real. The jets exist. The geometry is measured. The energy budget doesn't balance. Those are facts, independent of interpretation. And facts, when they contradict expectations, are the most valuable kind. They tell you your understanding is incomplete. They point toward new physics, new chemistry, new possibilities you hadn't considered. Even if 3I/Atlas turns out to be entirely natural, the process of explaining it will expand our knowledge of cometary behaviour, outgassing mechanisms, perhaps even exotic ice compositions or internal structures we didn't know were possible. So here's what comes next. You wait. You watch. December 19th arrives, the data floods in, and teams around the world analyse it. Papers get written, conferences happen, debates rage. Slowly, over months and years, a picture emerges. Maybe it's clear, maybe it's murky, but it's more complete than what we have now. And in the meantime, the search continues. Rubin Observatory comes online. More interstellar objects get discovered. Each one gets scrutinized with the same intensity, the same openness to unconventional explanations. Because that's what 3I/Atlas has taught us. Don't assume, test, don't dismiss, investigate. The universe is full of mysteries. Some are natural wonders. Phenomena we'll eventually understand through better physics and more refined observations. Some might be something else. Artifacts, messages. Evidence of minds that aren't human but share our curiosity, our drive to explore, our refusal to accept the limits of our birthplace. You look at the night sky one more time. 3I/Atlas is out there, invisible but real, carrying secrets we're trying to decode. In a few weeks, our best instruments will turn toward it and capture the clearest data we've ever obtained. And you'll be watching. The world will be watching. Because this moment, right now, is when humanity stopped assuming we're alone and started genuinely looking for evidence of others. Whether we find it with 3I/Atlas or some future object doesn't change the importance of asking the question. The search has begun. The bet is on. And the universe, as always, holds more answers than we have questions for. We just have to be brave enough to ask.